Hi guys, so we've got a power supply here, ATX Power Supply, which is faulty, and it's a 600 watt one. Got some useful outputs on it, IDE, SATA, the various 6 ways, a couple of them 8 ways, 4 ways. Probably useful as a test power supply around the workshop at least. So I thought I'd try and fix this. Basically what's happening with it is, it's going to turn the power off. So this is a vary. I can have a power switch here which I can turn mains on and off, and this is a light bulb up here. I'll just switch it to the light bulb, and it's wired like this. Hopefully you've seen this before, so I won't show you very more than quickly unless you use this video, but mains in, mains out, and it goes via the light bulb. When the switch is open, the mains goes via the light bulb. So if you connect a device from here to here and it happens to be short circuit, when you turn the power on, the light bulb comes on. Nothing goes bang, you don't need a new pair of trousers, you know, nothing's scaring you. That's all it does. Of course you can close the switch and then the power goes direct through, yeah? So I've already tested this if you saw the previous video, but quickly again, we're going to power it up without any load. Because if nothing else, the ATX power supply should give us the 5 volt standby. So I'm going to connect the black lead of the meter to one of the black terminals, doesn't matter which one. I'm going to connect the other red to the purple, which is here, fourth one in from this end on the 24-way connector. Okay, we get a test meter, we'll stick it to volts. And we're just going to switch this on and see what we get. So if you watch the light bulb up here, you'll see, first of all, you'll see I need to actually plug the power in, the mains, yeah? So let's give it mains. Power switch on the back of it's turned on. So when I turn this on, as you'll see what's going to happen, the light bulb comes on bright. And we have no 5 volt standby. That's not normal. And the fan also, if you notice, the fan didn't budge or anything. Yeah, nothing. That's not normal. What you would expect to see normally is the light bulb will come on bright for an instance and then go dim, because the power supply is sort of charged the capacitors. That's the light going bright. Then it goes dim because only the standby is running, and you'll see 5 volts here. So we have a duff power supply. So let's rearrange the bench, and then we can open it up and have a look to see what we have here. I'm just going to disconnect the power first for safety. Okay, so I'll just rearrange the workbench. Okay, so here's our power supply. First thing we're going to have to do with this is to open it up, obviously. Seems to be just 4 screws here. These hold the fans in. So we'll take these out. And let's have a look, see what we've got inside it, eh? Let's see what's in here. Okay, that's those out. There's probably some, well, there's a warranty seal, so it's obviously, I know it has been opened before, because was it? No, the warranty seal was intact, so it's not been opened before. I think probably that might actually just come apart. Anything else holding this together? Can't see anything. Okay, let's see if actually we can get inside this. No, it's coming apart. There's no other screws holding this together, so there we go. It's apart. So there we have our power supply. Now the first thing you'll notice is that it's very difficult to get inside here to do anything. You know, this is not going to be an easy thing to work on like this. So what I would normally do next to the ATX power supply is to get the circuit board out of the unit, yeah? Just before I do that, there are some big capacitors in here which could be charged up to a high voltage. I know in this instance they're not, because the light bulb goes off basically. You know, I know this is drawing power, so these are not going to charge up. But as a standard thing, I would actually check now to be sure that there's no voltage on any of either of these big heat sinks, yeah? Because depending on the design, they could be live. So we'll check to ground on the low voltage and on the high voltage side. So what I'm going to do is first just on the low voltage side, resistance, no sorry, voltage, just be sure there's no voltage on any of these, no. We can also test the high voltage side, so I'm going to test the negative, no, say negative I mean neutral, and I'm going to connect to the live if I can find the live down under there. Yeah, it's easy getting to the socket here. No. So there's no voltage in there. That's the first thing we need to be certain. You're more likely to have a dangerous situation if the light bulb lights up bright, for instance, and goes off, and nothing powers up. Okay, so we need to figure out how to get this lot out of here. This has a fan, so this is probably just held on by a plug-in connector. So first of all, there's a cable tie on here that's just holding all that together. Yeah. Let's get the camera a little bit closer in so you can see what you need to see. Okay, one moment. I'll do it off. Save making you feel seasick. So all I've done is I've just taken a little cable tie off here to free these wires up. I can see now that these are actually connecting to a little plug under here. So let's see if we can just disconnect that. Otherwise, I'll take these two screws out that holds this board on first. If I can't. So let's get this little PCB off here. Now we're convinced this is safe to work on, obviously. Put all these screws on one side where they're not going to get lost in the little plastic tub. Okay. Come out. It's coming with a little bit of effort. Let's try a small screwdriver that fits it a little bit better. Okay. So we can get this out of the way. This is probably held in by glue. I may need to break the seal on the glue, but let's have a go. Yeah, it's held in with a bit of glue. Down the sides of here, yeah, normally. So what I normally do here is get like a soldering tool with a little blade end and just kind of push it down either side of these. That should break the seal, and then I should be able to leave it. Yeah, there we go. If you don't do that and you pull, you'll probably take this plastic piece off as well and just leave the two pins in the board. So it's easiest to do it that way. There's also another wire here. Where's this going to? Oh, I see. So there's another output over here which comes from basically from the fan. Must have a 12 volt output on here, I guess. I wonder if this is designed so we can control this fan from a motherboard. That's interesting. It's a bit unusual, that is. Okay. I'll have to take this big cable tie off here. There. Now we should be able to start to get some of these wires out from here. We need to get them all out. There's a cable tie on the inside as well. So take that one off. Yeah. That's it. Now we can start to get these out of here. There's the plastic cable tie, yeah. Okay. That's all the wires out from the case. Now, the next thing we need to do is disconnect the mains coming in. Sometimes you have to unsolder it from the board, but in this case, it just seems to be this one plug, leaving the plug on the board. So, with a bit of luck now, there's a capacitor here that appears to be attached to this top bit, yeah. There's an earth tag here, which I think easiest thing I will just unsolder. So I want to free all the wires so I can get this circuit board out of the casing. I can just switch the soldering iron on. This should be quite easy to unsolder. One moment, let it go bleep. There you go. Did you hear the bleep? But it went bleep. So, okay, we've desoldered the earth wire from there. There's another capacitor here which is just attached to this. I can see it's just attached to this. I may have to take this back panel off. I may not. Let's see if we can get the board out. Okay, so the board's going to be held in by a number of screws. I can see 2 here, 1 there, and a couple on the other side. So let's take the visible screws out and see whether we can actually get this PCB out of the casing. So that one. Another one, 2 over here. So that one. There's 2 I can see this side. 1. Let's get the other one underneath all these wires. Here we go. That's down in this corner. Okay, that's those out. Is this circuit board now free to move? Yeah, partly. Getting there, shall we say. Looks like I have to unsolder another wire from here to get rid of that, but still we'll do that in a minute. I can see another screw. It's tucked down. Ow, ouch! That's a fingernail, bent. It's tucked down here. I don't know if you can just see it there. Yeah, that hurt. I have to trim that nail. It didn't. It didn't actually break, but it just bent it backwards. It was a bit painful. Okay, let's have this screw out of here. There we go. Okay, now it's loose, and we can see now there's actually 2 PCBs here. 1, 2, yeah. Okay. Put that somewhere. You just see that. This is the input. So all you got here, by the way. Sorry, it's obviously got the on-off switch, the power coming in through a filter coil, a couple of capacitors across the power. Couple of little capacitors there to earth either side, and then this goes to the board. But we know that's working because we know there was power getting in, so that can go on one side. Let's see what we have here. First of all, let's get rid of this. It's only going to be in our way. There's one wire that just holds it in place on here. So I can unsolder that. Make a note of where it comes from first, because it's surprising. You think it's obvious until you can put it back together and you can't quite remember. Although you usually can see where you've been desoldering, but let's just do this properly so we can see that there's the black wire coming in here. And I'm just going to take a photograph of that. Yeah, just a little photograph. Always worth doing that when you're desoldering stuff, or sometimes even when you're dismantling stuff, if you want to, be sure you know how it came apart, because hopefully you're going to fix it and put it back together. Okay, let's get a bit of solder on this. I can see where it's coming in here. Little leaded solder. There's a blob of solder, and this now should just literally just pull off. Yep, out it comes. Okay. In fact, while I'm at it, let's just clean that bit of board as well, then we'll definitely know where it came from. Bit of braid. Possibly need flux to do this, but we can have a go. Yeah, it's come. No, it hasn't come. Okay, let's have a bit of flux, because we'll have to do this sooner or later anyway, most likely. Bit of flux. Let's have another go at that, just clean it up. Yeah. So I've cleaned that hole. We can now remove this, the fan, on one side. Now we've got to get into what we wanted. Okay, don't need the cutters for the moment, don't need the screwdrivers anymore for the moment. Yeah, get your bench tidy, you know, don't need the tool, don't need the braid, don't need the solder right now. So let's just tidy all that up, get a nice clean bench to work on. What else we got here? Some them, yeah, zip ties. Obviously we'll need to put new ones, they can go in the bin. Right, one more tool. The reason I do this is you'd be surprised, one of these days you're going to get sort of two or something underneath one of these things and turn it on with power on. And you're going to end up with more problems when you started. Okay, what do we have? Well, it looks reasonably well made. Yeah, it doesn't seem to be you know, like one of these things made for the cheapest possible cost. We have here, this is nice actually to show you this one. The power comes in here. Yeah, power comes in here. Let's find the pointer. Power comes in here, yeah. Through a fuse, here you can see a fuse. This will be a thermometer, negative temperature coefficient. So when you first switch on, that has a relatively high resistance. As the current passes through it, it warms up and the resistance goes down. The idea is that when you first plug that in, these big capacitors, which will basically look like a short until they start to charge up, they don't blow the fuse. You know, like you get a big massive surge current when you first switch it on, yeah? This is why, by the way, when you have the light bulb on a good one, you see it to flash once and go off. So once bright and then dims, and it's just these charging. So this is to limit the current of that. More capacitors strapped across the input and coil. This is just stop interference, getting back into the mains wiring. And it's all tied up in a knot with my microphone lead. There you go. Okay. This thing is usually on the same PCB. In this case it was tucked down here. Quite often this third heatsink is on the main board, yeah? This is called PFC, power factor correction. We can look at the PFC circuit while we're doing the repair, but basically it's a bit like a switch mode power supply using FETs, two of them here, big FETs, and a controller chip, yeah? And it's basically switching these on and off very rapidly and sending the signal through a coil somewhere. This is the input coil. Probably the coil down there. What will be one of the coils? Probably this one down here. Maybe this one. What may well be this one actually. So it kind of like switches very rapidly through the coil, and it basically is to make the thing more efficient. You can go and look up power factor and power factor correction and why you need it. Basically, to say from the point of view repair, first of all, you don't actually need it. You can generally take this out of the circuit and bypass it. So on here you'll kind of like power coming in and power going back out, yeah, through the PFC circuit. And it's possible to actually take this out to bridge it out, you know, and not have it. All that will do effectively is reduce the efficiency of the thing, but it won't actually affect the working of it normally. So that's something you can do if you need to, yeah. But generally you should leave these things in, obviously. We see some capacitors down here which are part of this circuit. One of these will probably be a startup. We'll probably find some high value resistors down here. We can look at this chip. We'll get a data sheet. Tucked in down here is your bridge rectifier. Yeah. This converts the incoming AC into DC. Once it's gone through the bridge rectifier, it'll go through the PFC, this coil, which is controlled by these, and it'll charge these big two capacitors. Okay, that's your first stage. Now here you have another big heatsink, yeah. 3 transformers I can see on this one. 1, 2, 3, and then another big heatsink, yeah. And then some more coils, lots of capacitors, and your power coming out. So basically, the way this works, let's see in case we want a camera in one go. Yeah, okay. Okay, so power comes in through the PFC into the power comes in through the bridge rectifier, converts it to DC through the PFC, which effectively, I'll show you what it does in a minute, and charges these capacitors, yeah? You've now got a high DC voltage on here, maybe 350 volts or towards 400, something like that, yeah, okay? These charge up to a high DC potential. We've now got 3 transformers. This is the big one. This will be driving your main output. So on this heatsink, you'll have FETs, power FETs, that are powering this transformer. Effectively, from this capacitor through the transformer and back to the negative, there's a FET and it's switching on and off very rapidly. There may well be 2 of them. It's 2 capacitors, I'll say there is 2 FETs running what's called a half bridge mode. But basically, these FETs are driving this transformer on the primary, yeah? Coming out the secondary, this big thick wire. On here are your rectifier diodes on your low voltage side, yeah? Then after that it's just smoothing. Lots and lots of capacitors and coils, inductors to smooth all the ripple and spikes so you get a nice DC coming out of here. That's effectively what we have here. Look underneath it. We have a big gap here, yeah? Can you see? You've got circuitry over here, a big gap and circuitry over here. Okay. This isolates the high voltage side from the low voltage side. So there's no physical connection between the 2 sides, yeah? All you have between the 2 sides are transformers. Yeah, big one, 2 smaller ones. And down here will be, these 4 pins will be an opto isolator. I'll show you the isolator. The isolator's down there, yeah? Can you see the thing with 4 pins? No. How this basically works is, this circuitry is driving the primary of the transformer, yeah? Of the main one and the other ones. This is effectively your low voltage side, and there'll be a feedback circuit from this side to this side. So when the voltage, it normally only monitors 1 rail, say the 5 volt rail. When the 5 volt rail is correct, in here is an LED, yeah? And the LED lights up, and on this side is a photo transistor that it basically is a transistor that turns on when you shine light on it. So inside the thing is an LED and a photo transistor. And this side will control the pulse width modulator, the controller for the switch mode power supply. It will control that and effectively say, okay, I've got enough voltage now, and this light backs off, yeah? And so on. That's how it does it, yeah? The way this controls the voltage coming through, how much voltage is coming out, is either 2 ways. One way is a pulse width modulator, so it's sending pulses into the primary of the transformer, yeah? And then effectively the wider the pulses, so there's more on time than off time, the more power it generates. The narrower the pulse, so it's more off time than there is on time, the less. So the frequency will stay the same, but the actual width of the pulse will vary. That's one way. The other way is actually varies the frequency, and this coil reacts differently at different frequencies and gives different voltages effectively. So it's one of 2 ways that'll be working. So, why are there 3 transformers? Usually there's 2, and normally I see 2. And the reason I normally see 2 is one of them, the big one, will be your main power supply, yeah? And the small one will be the standby power supply, the 5 volt standby. And the standby will have its own controller, and the big power supply will have its own controller and driver, yeah? And effectively, when you switch on, the standby power supply is always running. That's what puts the 5 volt standby onto the ATX connector, yeah? On here. On the purple wire, yeah? This starts your motherboard up, and when you press the power on switch on the motherboard, it connects this green wire to ground, and that green wire signals the big power supply in here to switch on. That's how it works. In our case, it's drawing power and we've got no standby. At this point, this big transformer shouldn't be running, it should be off. All the circuitry that drives this should be off, it shouldn't be working until we press the button. And even if we had it connected to a computer, we couldn't press the button because there's no standby, so it wouldn't do anything. So the first thing I need to do this is initially to see if I can find the standby controller, yeah? And we're going to check for some short circuits on this as well to see if we have any obvious shorts. So I'm just going to zoom out the camera and let's have a look to see what we can find. Okay, So the first place to start looking for shorts, which is on bleep mode, yeah, is where the power comes in. Yeah, we disconnected the mains power. You'd expect this to be open circuit. I'll even put it on resistance range. We shouldn't expect to see any, or an extremely very high. We saw a little bit as the capacitors are charging. Yeah, it's already 5 mega ohms. So here we're seeing very high resistance. So we don't have a short there. Second place is going to be on these big capacitors, yeah? So these will start off as a low value, and as they charge up, it'll increase. Yeah, we're up to 35 kilo ohms already. So there's no low resistance there. This is the other one. Just charging up, yeah. So there's no short across either of the big capacitors. Next place. Okay, the other place you might have shorts is on this heatsink. These are your rectifier diodes. Easiest place to check that without taking the thing off is probably just to see if you've got any shorts on the outputs, yeah, to ground, 5 volt, 12 volt, 3 volt. Because if you had a short circuit diode there, you would expect probably to see the short circuit here. If I see any short circuits here, that's something else suspicious. If I don't, there probably isn't a short there. That reads low. That reads low. We have a lot of things that read low on this. It's a bit high. There's something suspicious there as well, so we have to tackle this bit now, bit by bit. Yeah, we seem to have lots of possible problems here that we need to go into. Okay, so let's start with the PFC. This is where I found a device, I think it was this one, that effectively reads like a diode both ways. I'm a bit suspicious of it. On here also is a control chip, yeah, and I will just get my magnifier to have a see what that is, rather than trying to. If I'd zoom it all the way down, I'm not sure if you'd see it. It's a L6562N, made by SGS Thompson. L6562N. Okay. L6562N. Make a note of that. L6562N. Let's make a note of that. Let's also try to remove this device. I can probably just unscrew it and slide it off. The other option would be just to unsolder the whole lot, in which case we can test the other devices. So because we seem to have a lot of problems on this, I'm actually going to unsolder this entire heatsink complete with the parts that are on it, yeah? Right, let's do that. So it's going to take some flux. Try first with flux and solder braid, yeah? And see where that gets us. If that doesn't get us anywhere, we'll use the vacuum desoldering machine. Get some flux on there. Secondly, let's get some solder on here. It's unusual, by the way, when you're looking at fault finding things, to find more than one problem. This seems to have a number of suspicious problems. I think we have to go through the whole thing to see what's going on with it, yeah, and just make sure that that things are working properly on the way. So let's get some heat into here. I'll switch the vacuum desoldering tool on so it's warming up, because we might well need it. So let's warm that up in the meantime, because it takes a while to warm up. By adding leaded solder to each of these, I'm making it easier for the solder braid to desolder them, yeah? Okay. Desoldering braid. See if we can get the solder off here. Okay, that one's clean. That's a good start. Continue with a bit of flux on the braid as well, which helps. That one looks like it's clean. And that one is clean. You can test this by just kind of like pushing with your soldering iron against the leg, yeah? See if it actually moves a little bit. No, that one isn't. That's still got solder on it. Let's try and get that one. Clean up the braid again. Let's give you a bit more zoom. Why not? I'd like you to be able to see what I'm doing. Okay, is that nice and clear for you? You can see what we're doing here. That's clear. It clicked. I heard it click. Next one. Bit of solder on the braid always helps. Also keep the thing clean. Get rid of the the shitty bit at the end. Let's have a go for this one. See if we can desolder it. I could use that. I mean, obviously I've got the vacuum desoldering tool, but let's see if we can do this with basic equipment. Because I'm guessing some of you guys have got fairly basic equipment. So let's see if it's doable, yeah. Okay, those two look clear to me. Okay, clean that off. Bit of flux. No, that seems to have got the third pin. Not 100% sure. Yeah, it looks like it's done. Yeah. Yeah, let's just get rid of that bit of braid. I used to think solder braid was a waste of time until I started using it with flux, and then I realised it works. But honestly, before I used it with flux, it didn't. It was rubbish. So try it yourself, but I'm pretty sure you'll find the same as me, that you need to use braid with flux before you can do anything useful with it. That's two of them. Let's get the third one. Not sure about that middle one. I think it's stuck on this side. Sorry guys. Yeah, that middle one seems to be stuck this side, yeah. Might be worth just trying the effects for just push it back a little bit. There we are. Now I think I actually broke the track by doing that. Seems to be a track here. So we need to look at that under magnification to see if we broke it. I don't think we have actually. I think that pad just goes like that. I think this is designed where you can have a device where they're 3 in a line, or 1, 2, 3, yeah? Because look, it doesn't go anywhere other than that. It doesn't go to here, for instance. Also, it wouldn't make any sense, because if it went to there, it would be shorted to that one, yeah? So that just goes like that. Okay. Let's see if it'll come off. It's loose. Something holding it at this end. Let's see. Easiest way to check this is just to see if these legs actually will move. That one's moving. That one's moving. That one's moving now. I can see all those are actually moving. Everything's moving. So what's all? Oh, that's what's holding this in place. There's a metal pin. Can you see it behind there? To there, yeah. That's why it won't come off. Okay, a bit of solder on that. This might take a bit of heating. I'll probably just try to remove it with what is that. Yeah, there you go, yeah. You fire often those pins onto the heatsink, they take a bit of, obviously, a heatsink. It's a heatsink, it sinks heat, yeah? They can be a bit difficult to remove. Once we've done that, though, now we can get rid of all this used braid, yeah? And we can just clean that up as well. Where was that pin coming through? Yeah, I can see it's here. Okay. Let's try it without the flux, but normally I think it needs the flux. If it's an empty hole, it might just come. Yeah, okay. So, let's see what we have. We have K2837, two of them, yeah? And this device here, which was reading a bit strange. Let's see if that still reads a bit strange now it's out of the circuit. So this was kind of like reading, let me see, where was it in the board, how many holes did it have? Sorry, out of here. It's obviously a 3-pin device, you can see clearly here. But these 2 pins are connecting together, yeah? So, from here to here, it's connected together. So, this should be like a diode. There's another diode, because I'm actually reading like a diode there. What happens if I go the other way? It reads like higher. Obviously short there. Let's have a look at our little device itself. So we're expecting from either outside to the middle to be like a diode, yeah? Nothing there. Yeah, that reads like a diode junction. That reads like a diode. So that reads okay. These things, K2837, they're either transistors or they're FETs. If they're transistors, from this end here, is probably the base collector emitter. Should read like a diode, which it doesn't, yeah? Go the other way. Doesn't. So these are probably FETs. We can try and test them as I did with the service mount ones off the V-core, which effectively is to touch the red to that one and see if these two become conducting. Yeah, it's a diode that way. Right, touch the red to that. It turned on, it's going to turn back off again, I think. Touch the black to that. Now it's off. Touch the red to the gate, and this will conduct. But obviously this FET loses the charge on the gate, yeah? It dissipates. So same with this one. Red onto there. Now let's see what happens. Yeah, it turns on and then it's turning off. All the way should be like a diode. Those look good. Let's use my component tester as well. Have you seen this thing before? Yeah. So what we do is with this, or we can do it on this camera, even easier. So we just connect the wires to the device in any order whatsoever, doesn't matter. Yeah. And we hit on, and it'll test it. Probably tells it's a FET. N-channel MOSFET, yeah? Which is kind of what we thought. Telling us which one, so the red's the gate, which we kind of determined, because we effectively switched these on with a meter. That's the threshold voltage required to turn the gate on, turn the FET on. That was the test current, so that's that one. So this is also telling us that these are good. Yeah, other one. Analysing. Yeah, another MOSFET. Again, it's telling you which one's which. Very slightly different voltage, that's nothing. Okay. So, those are FETs. The last one, I'm expecting will tell us it's either a diode or a diode junction, yeah? Yeah, put them on any order you want, doesn't matter. Analysing. A common cathode diode network. So it's basically two diodes. The anodes on either end, and then both cathodes connected to the middle one. We can actually check that as well, to be sure. You're not in the rush, are you guys? You're not in the rush with this repair? No? Good. Okay, let's have a look to see what that actually is. Where's my magnifier? it's a ER1606CT. You can't see this. I wish I could show you this. I've got the microscope. We don't need to look it up, and I'm going to show you why we don't need to look it up. Just go over to the microscope. See if the microscope cam's actually working. No? Okay, one moment. Okay guys, so that's why we don't need to look up the data sheet. You can see the part number now, and you can see on it, it's a common cathode diode network. So all those devices check okay, but they were reading a little bit strange in that circuit to my mind, and I'd be interested to see if we can see what the controller chip is on that power factor correction PFC circuit, and also so you can have a look to see what that circuit should look like, yeah, to give you some idea. Okay, let's go back over to the main camera. Okay, so you can see now we've taken the thing out. In fact, these were marked D5 for diode, Q1 and Q2, yeah, and we have a controller chip down here. So let's have a look at that controller chip and look for a data sheet and see what it tells us about that. We'll get back under the microscope so we can actually get the part number. Okay, you can see yourself now the SGS Thompson logo, and it's upside down, but you can see L6562N. And this is what I was reading with the eyeglass, but you can see yourself now. So let's have a look for that, 6562N, and see if we can see what it is and a typical circuit. And hopefully the typical circuit will be something like we have on here, and we can possibly work out whether the funny readings around this diode are actually okay. Hi guys, girls. Okay, so I recorded the first part of this video yesterday, and last night I was just checking through, editing anything I needed, just make sure everything was okay, really. And I noticed that I cocked up on that recording. I paused the camera when I didn't pause it when I thought I had, and then I paused it when I thought I hadn't, and I lost a chunk of the recording. But no worries, I can briefly go over what was happening and what I found on that missing bit. I'm not quite sure, well, I know you missed a chunk of it. So the first thing I know that you did miss was looking around this board. This is the PFC, power factor correction circuit, and what I noticed, I've now removed this, as you know, but when this diode was in place here, I could see across the diode with my diode tester, I could see a diode junction in both directions, like positive to negative and negative to positive, and that, I said, was suspicious. It didn't look right. I shouldn't get a reading both ways on a diode like that, or at least I need to investigate why I've got a reading both ways on a diode like that. So that's why I then removed the heatsink with the components, the two power FETs and the diode, which is a diode matrix basically, and I found they're okay. Yeah, they're okay. The second part of the recording I think you missed. After I checked that, I said, okay, that's the first section of the power supply, yeah? And what this basically does is, and we'll look at the circuit again in a minute, but what this does is, it takes the mains coming in, the 240 volts, and it's basically as a booster. It boosts the voltage up to about 400 volts or thereabouts on to the big capacitors here, yeah? So these capacitors, I don't know if you can just see down here, you can probably see the start of the writing. They say 200 volts, yeah? I can't just see the microfarads. Oh, 1000 microfarads, 200 volts, and there's two of them, yeah? And because I know this circuit was got 240 volts coming in to start with, so you'd expect them to charge to 300, and this boosts it up even higher than that. So I'm sure what we have here are two capacitors in series, yeah? So effectively using 1000 microfarad times 200, two of them, gives you 500 microfarads at 400 volts. I explained this on one of the videos I did on capacitors, so I'll link to that video on this one. Go and check it out if you didn't watch the video on capacitors. It's an interesting one. Okay, so we checked that. When you've got your 400 volts in here, this next section of the power supply, this big heatsink here, and you can probably see down here there's a number of devices bolted to the heatsink, yeah? This section drives the transformer or transformers. Normally there's a big transformer and one small. So the big transformer is for all your output voltages, and then the small is for your standby, and they're individually controlled. So the small power supply runs all the time, and the big one runs when it's, you know, when you effectively switch the button on the ATX switch, it turns the big one on. This, I've got 3 transformers. I don't exactly know why. It's possible one of them, this one, is just driving the 12 volts and the others are driving the 5 and 3.3, because generally the 12 volt needs more current. But then one would also be driving somewhere the standby, and I still haven't, unless one of these is standby. I don't know. This one's slightly smaller than this one, I think. No, maybe they're the same. But anyway, we have 3 transformers and they're being driven by this. If I need to, I can work out what transformer is doing what quite easily, and I'll show you how to do it. So, the next place to look for short circuits would be on this drive circuitry into the transformers, into the primary of the transformers. Yeah. Again, I did a video on inductors and transformers. I'll link it on this one. If you didn't watch it, I suggest you do watch that. It'll help you to understand a lot of these circuits much better. Looking on the back of the board, I can see here some big thick legs, 1, 2, 3, yeah, and 1, 2, 3 again. And those are probably, you can see they look like square, yeah. 1, 2, 3. You can see those definitely, and these not quite so clear, but you can see them. And then some smaller ones here, yeah. These will be power devices on this heatsink. And the next place to look for shorts would be here. So I've got the meter in the top corner over here. I'm on diode mode. I'm just going to look on the legs of these. And I do see what look like short circuits here. Not between those pins, but certainly, I think it wasn't even on the device. There. There's lots of shorts around here. That would suggest that there's a problem in this region. But also, we have the funny readings on the PFC, yeah? So that was worth looking at. The other thing I found with this is the output, yeah? So if we just connect to ground and we go on here to the yellow ones are the 12 volt, yeah? 12 volt output. I can see a voltage climbing. That's like a capacitor's charging on that rail. So there's no short on the 12 volt, yeah? Orange ones are 3.3. They appear to have a short on the 3.3, yeah? And the red ones are going to be 5 volt. That has a very low resistance. Not quite as short like that one, but even so, it's very low resistance. So there seems to be a problem with that. And the last one we'll look at the standby. The purple wire, capacitor charge again. That appears to be okay. So we seem to have a problem on the output on the 3 and the 5 volt, possibly short. We seem to have short circuits in this region, yeah, and we seem to have some funny readings on the PFC board. Okay, so let's have a look at the circuit now. First for the PFC. Let's look at this section, then we'll go to this section, and then we'll go to this section, yeah. I'd say this is a bit unusual if what I'm seeing is correct, of multiple faults, because normally speaking, when something goes wrong, it's one component that goes wrong and just stops it working. But in this case, we seem to maybe have multiple problems, yeah? Maybe something's blown and then taking a lot of other things out with it. So, let's have a look at the circuit that we were looking at yesterday for the power factor correction. And I'll explain a little bit better now how this actually works. Okay. So this is from the data sheet. We have the data sheet for the chip on the PFC board, the L6562N, and this is a typical application on the data sheet. And I want to explain to you how this is basically working, and then we can look on our PFC board and see if we can make sense of any of the readings. Yeah. So this is a bridge rectifier. Here we have AC coming in, 85 to 265 volts. Yeah. And this converts the AC to a pulsed DC. It's not exactly smooth. It's like AC is like this, yeah, up, down. And this kind of like it gives you the top half, and then the half of the side when it goes down, it inverts it, so you get the top half again. So effectively, AC is 50 or 60 hertz. Yeah, here we have lots of positive lumps, if you like, halves of sine waves at twice the frequency, 100 or 120 hertz. So you can see here it's saying plus and minus. Yeah, can you see on the bridge rectifier, a little plus and minus that? The minus just goes to what you call ground, but this is not ground. This is what's called hot ground. It has this funny black blob symbol rather than the 3 lines, which is ground. The reason it's not ground, I mean, it's ground to this circuit. It's the ground reference point for this circuit, but it's not ground. It's not a safe ground. And the reason being, if you look at this, when the AC comes in, yeah, on the positive half cycle, this diode conducts, yeah, and the power goes up that way. When this part is positive, because you take it in turns, positive, positive, it switches around, plus, minus, minus, plus. So when this end is plus, that diode conducts into the power, yeah? When this end is plus, this diode conducts. The diodes conduct in the direction of the arrow in the symbol, yeah? I always remember it's just in the direction of the arrow. That's conventional current, and that's the way it goes, in the direction of the arrow, yeah? Look what happens on a negative half cycle. When this end is negative, this diode conducts, yeah, and that connects to hot ground. When this end is negative, this diode conducts to hot ground, yeah. So this ground here, basically 50% of the time it's connected to live and 50% of the time it's connected to neutral. They used to call this half mains voltage. What they mean is the full mains voltage half of the time when it's connecting to live, yeah. So you need to be aware, you can't connect anything grounded to here. Don't connect an oscilloscope or anything else that's grounded to this point. Because if you do, if you connect ground to here from a test equipment, instantly you're going to blow one of these diodes in the bridge rectifier, or blow the fuse, or blow both, and trip out your mains power as well. Most likely it'll save you. But remember, this hot ground, you can connect a test meter to it because it's not grounded, yeah. But any device, like a USB device, any test equipment that's got a ground on, like an oscilloscope, you can't, okay? There is a way around that. We'll talk about the way around it later. There is a way where you can connect an oscilloscope to here, but for now, let's say you can't, okay? Right, safety talk. Right, let's back to the circuit. So your AC comes in here, positive of this side rectifier and negative is this, going to, in inverted commas, ground, yeah? Right. Power comes in through here. Now it's got 2 ways to go. One way, it flows through this inductor, through this diode, through this negative temperature coefficient thermistor, which starts at 2.5 ohms, and it charges the capacitor. As this thermistor gets warm, because it will warm up, the resistance decreases until it becomes practically 0. This is to stop a massive inrush of current when you first switch on, which might blow one of these diodes, or this diode, for instance, yeah? Right. The other way it can flow is in here, through this diode, which bypasses the coil, through the NTC, and charge the capacitor. So as soon as you plug in the capacitor, the big, this is the 2 that we had 200 volt 1000 orphan series, yeah? So we had 2 in series here. They start to charge up. This chip here actually gets power via these 2 high value resistors. You've probably seen this on switch modes I've shown you before. And this initially starts to power the chip. It's got a capacitor here. This powers this up, yeah. It's also got a connection from here as well, and a connection back from the transformer winding here. But this is where this chip powers up, yeah. This chip starts to switch this FET on and off rapidly. In our case, there's 2 FETs in parallel sharing the load, yeah. They switch it on and off rapidly. And they're connecting this end of the coil, which effectively got positive high voltage on, through these 2 low value resistors. So we've got 0.33 and 0.33 in parallel, gives us about 0.16, yeah. 1 watt each, so 2 watt. So they're connecting this, switches on, and connects this point through these resistors to ground, okay. These resistors, by the way, when the current flows through them, it generates a voltage across, and this here is a current sensor on pin 4. If we go and look at the inputs for the chip, we'll see. In fact, yeah, let's do that. Don't take my word for this. Don't take my word for all of it. Pin 3, pin 4. Pin 3 connected to the rectifier mains voltage via resistor divider. That's picking up a signal from the mains, basically. It's not the power coming in. we have pin 4. Pin 8 is the power coming in. Let's make a note of that. Pin 8 is the power coming in, yeah? And let's find the current sensor as well. CS pin 4. We said pin 4, yeah? Pin 4 input to the pulse width modulator. The current flowing in the MOSFET is sensed through a resistor in case we have 2 resistors in parallel. So pin 4 and pin 8 is the power. Pin 4 sensors through the resistors off the FET, yeah? This is your power coming in this way, yeah? This actually detects where we are on the sine wave or the half sine wave to help this switch this on and off at the right time. So this is switching on and off. It's got power, yeah, it's got a current sensor, it's got ground, hot ground, yeah. This is switching on and off rapidly. Now, if you watch the video I did on inductors, you'll see that an inductor is kind of like a flywheel, yeah. We did a perfect explanation of this using the water wheel and water. If you've not watched the inductor video, you need to watch it. If you don't watch that one video, at least the first 20 minutes, you're not going to be able to understand these circuits properly. So you really need to watch it, and I'll link again that video onto this one. But basically, every time this switch is on, it draws power through this coil to ground. Yeah? It grounds effectively this end of the coil, and it only does it for a very short amount of time, microseconds. Yeah. Before the current can build up through here, this actually goes bang, it switches off again. And if you watch the video, I'm going to link, you'll understand that when this switches back off, the polarity on this coil reverses and this end becomes the positive and it discharges the magnetic field. And this end now is positive compared with this end, yeah? Originally this end was positive, let's say 250 volts, yeah? When the switch is off, this end becomes positive, it becomes more positive. That positive voltage now, look where it goes. It can't go back through the bridge rectifier because there's only pass current in the direction of the arrow. So it can't go down there, but where it can go is through this diode and into the capacitors, yeah? Charging them up. It can't come through this one because it's only conducting the direction of the arrow. So the only place that high voltage can go is through this diode and into the capacitor, and that's your boost. That's what boosts the voltage up here to 400 volts by continually switching this on off and drawing current one way through this inductor, then letting it fly back. It's called fly, but let it fly back the other way. That's what boosts the voltage here. Yeah, there you go. That's how it works. When it's first powering up, you'll see obviously before this starts running, power can go through this diode and initially charge this capacitor. So by the time this starts running, there's already some charge in here, probably up to 250 volts by then, yeah? Okay, so this other winding, I'll just show you. This is a sensor. This pin here, 5, uses this winding to sense when this coil is magnetized and when it's fully demagnetized. And you can see that again if we go to the chip. Pin 5, boost inductors demagnetization sensing input for transmission mode operation. So basically, it's telling you there that when effectively this signal goes down, because there's no magnetism in it anymore, it triggers the MOSFET to turn on. The MOSFET being this, yeah. So this senses when the coil, this big coil, this is like a second small one. This senses when it's demagnetized, when it's empty of charge effectively. When the water wheel has stopped spinning. If you watch my other video, please do. And then this tells it to turn this FET back on again. Again, it draws power. Power builds up through here, and before the current can build up to the point where this would go bang, it switches off again. That's what this current sense resistor is doing. It's telling it effectively when to switch this back off. So that's how it works. Backwards and forwards, and your boost is coming here. If that isn't clear to you, please ask in the comments below. But before you ask, please do watch the video on inductors and capacitors, really, to understand it, yeah? Okay, so that's probably very close to the circuit we've got. So let's see if we can relate this to our circuit board and explain the readings we're seeing, okay? So I'll minimize this. Let's go back over to the desk cam again. Okay. To save keeping this all in your head, I've also printed this out. So I've actually printed out the circuit we were looking at. Let's try this with the camera zoomed out a little bit more and see if we can make some sense of it. One moment. Okay, so this is our board, and this is the circuit diagram. So what I noticed first was across this diode here, which is this one in the circuit, there's effectively reading the diode junction across it both ways, either polarity, which when I switch the wires round, I was reading both ways. The two outer pins, and those 3 pins, the two outer pins are connected together. So that's pin 1, and the middle one is pin 2. There's only actually 2 terminals on. Electrically, there's only 2 terminals on it. It actually has 2 diodes, one going from here to there, and one from there to there, working in parallel. So we removed the various the heatsink with the 3 components on. We tested all these and they're all okay. But I still, if I look on here, I'm on diode mode. Yeah, just shorted the leads. If we look here, I still see in one direction a diode junction. And then the other way I see this strange reading. And that doesn't look normal, basically. So we need to figure out why that is. So what you have here is 3 wires coming in, yeah? I've traced them through. The red one is going to the positive of the bridge rectifier, which is here, and the black one goes to the negative of the bridge rectifier. I can show you that. So the red wire goes to the positive of the bridge, and the black one goes to, sorry, the negative of the bridge, yeah? So this is your bridge rectifier. Let's mark it on the board, just make life so we can see it's even clearer. I had a marker pen, yeah, okay. So this end I marked in blue, that's minus, yeah? And this end is plus, yeah? So what we have is to check a bridge rectifier. We can check this. We go to one of the AC, so the AC is the 2 middle, doesn't matter which one. We go to one of them, yeah? And that AC should connect in one direction through a diode to one end, and in the other direction, when I say direction I mean reverse polarity if your meter leads to the other one, yeah? So this is the black lead, so that should conduct to the negative end if it's this input, and the negative end if it's this input, yeah, all that input. So that one there, that's coming through your diode, yeah? You see it 0.495. What you're seeing is the voltage drop of the diode. We'll talk about diodes in the next tutorial theory. That's the other one. Slightly different reading, but you know, diodes vary a little bit. 0.005 volt, not much. So those two are the 2 diodes that you see there and there. Oh, sorry, there and there, yeah? So if you look at the other input, positive on the AC should go to this end. There's one diode, and there's the other, yeah? If we put negative here, it won't conduct to this diode, there's nothing there, okay? But you're seeing some strange voltage there, 1005, and you shouldn't see anything, it should be nothing. The same happens if I put negative here and go positive on these. You shouldn't see anything. That should be nothing, yeah? So that's the first thing we notice. Second thing we notice, if we go across positive and negative of the bridge rectifier, that's from here to here, we shouldn't see anything. If anything, we should see this. We should see this capacitor charge up. That's all we should see. But we shouldn't see any conduction. Once that's charged up, we shouldn't see anything. So if I go directly across this bridge rectifier, I'm seeing a diode, 0.525. And the other way, I'm seeing this strange voltage, and that isn't right. We shouldn't see anything there, apart from maybe a capacitor charging. So, why, positive to negative, are we seeing a diode? If I go to resistance mode, okay, I'm on resistance mode now, and measure again across the bridge rectifier. Now I see a very high resistance, like, you know, that's 600 kilo ohms this way. High resistance again, 600 kilo ohms. So it's only on the diode mode I see a diode junction. This suggests basically the only reason you would see a diode junction is this. Connecting to this bridge rectifier, yeah, is a diode. That way, yeah. And the other end of the diode is short circuited to ground. Okay? Then from here to there you would see a diode junction. Well, let's have a look at what we've got on here on our circuit. We've removed this diode. We've taken this out. That's on the heatsink, yeah? That's not there anymore. This isn't there anymore. So we can't have a short down here because it's not there anymore, yeah? This is not there anymore, so nothing can flow that way. But we do have a diode here. This one. And one end of the diode is connected to the bridge rectifier, positive. And the other end should go to the positive end of the big capacitor. And there shouldn't be a connection from there to ground. So we can look at that and we can see what we actually have, yeah? So the diode is actually, can we see, let's get this in a position. You can probably just see the end of it there, yeah? If you look down here you can probably just see one end of the diode and the other end of it is here, yeah? And this diode, we can see it sideways now. We can let's get a bit of light in here, eh? Why not see it properly? You see it now, can't you? There it is, there's the diode, yeah. So we'll check this diode. The black to the, so the red to the cathode, the one with the stripe, it shouldn't conduct. And we've got a funny reading. Yeah? The other way, if it's a good diode, it should look like a diode junction. And it does. 0.521. Back across the bridge rectifier. It's practically what we see there, 0.525. So the only reason you would see this diode junction here is if this end of this here is shorted to here, yeah? And this end goes to the big capacitors. And here's our capacitors, yeah, 1, 2. You can see underneath, kind of let's turn it around so you can see it. Yeah, you can see this end's negative, negative, yeah. So basically the brown wire is the output from this, yeah. You can see, you can trace it through. You can see that this brown wire connects to this point here, yeah, at the output of this capacitor. So effectively that wire, that brown wire, is there, yeah. That's easy to just, you can get your test because you follow that through. We'll do it. Let's do it. We'll go from the brown wire, yeah, which is here, to top of this capacitor, and it's connected to it. Okay, so this is the first capacitor, and there's no short there. It's charging up, huh? And this is the second capacitor, and there's no short there. It's charging up, yeah. And this capacitor goes back to the negative end of the bridge rectifier. But if we go across both, you'll see we have a short. Yeah. So what we're seeing really, let's put it on our circuit diagram so it's absolutely clear what we're seeing here. We don't have this quite like this. What we have is that, yeah. This is the brown wire, yeah. From the brown wire goes to the top of the capacitor, yeah. This goes to the second capacitor, and that one goes to ground. So from here to here on the test meter, there's no short. We just see the capacitor charging up. The same applies from here to here. We don't see a short, just the capacitor charging up. But from here to here, we've got a short. Now, can you see now, when we measure from this bridge rectifier, we're seeing a diode junction. What we're seeing is through here, through this diode, through the brown wire, and across the short circuit. The short circuit is there, end to end. So that now is our circuit, yeah? Top of the bridge rectifier, through the diode, this is what the diode that we're seeing, through the brown wire, through the short, and back to the negative end of the rectifier. That's the short. Now we've come around the long way round to this now, because we kind of know where the short is, we were paying attention earlier. These big capacitors here are connected to these power devices on this heatsink here. We'll find the datasheet for the controller that drives this, and we'll see the circuit again, like I showed you the PFC. And we know, because we can see the ends of the devices here, yeah, the three legs. This is one of them, and this reads, there's possibly a short there, something going on, possibly a short, yeah, between those two. This reads short everywhere, and this reads short everywhere, yeah, and these are connected to these big capacitors somewhere, yeah, it's connected to there. It's all everything's short, and the chances are, when something goes short, the most likely thing to go short in this type of circuit, to start with, is the output devices. The same with amplifiers. If you've got an amplifier and there's a short circuit, it's most likely to be the biggest components on there, the output transistors or IC. If you've got a short on something like this, it's most likely to be the power transistors or FETs. Because they're doing the most work and in the position where the most current can flow, when something goes wrong, they're most likely to go short. So the next thing we're going to do with this is to remove this heatsink and the device. With the devices around it, I'll probably do the same I did before. I'm looking down here, I can see 1, 2, 3 devices on it, which we can see as 1, 2, 3. So those are the devices, and there'll no doubt be a metal pin that goes through the board. I think I'll pause the video because you've watched me remove this one, yeah? And the process is the same, so you don't really need to watch it again. So I'll pause the video and we'll get that off, and then let's have a look to see what we've got. Actually guys, just before I do that, just to prove what we were just talking about that short on these output devices giving a funny reading on the bridge rectifier, I've just disconnected the brown wire, yeah? So I've broken the circuit here. So this is no longer connected to the diode, yeah? And now let's go back and read across this bridge rectifier again. So this way round we saw a diode junction reading 0.5. Now it's reading nothing, yeah? The other way round I still read this funny voltage, and I'm not sure exactly what that is doing that, but I'm not too worried about that, and I'll tell you why. When I'm this way round, this is negative leader ammeter, yeah? So this end is negative, this end's positive. But in reality, that can't happen with the bridge rectifier. This end is always positive related to this end, and when I'm on the correct way round, I don't see that funny voltage. So it's of some concern. I'm a little bit interested to see why that's doing that, but I'm not overly just worried about it at the moment. If we're still having problems around here later, we'll just keep it in mind, yeah? Okay, now I'm going to desolder those other devices. Okay, so I removed the heatsink. Same way as I did the other one, this just had 2 metal tabs on, made it a little bit more difficult, but it was the same method. So on here we can see some transistors, 2SC3320, and one that says 3866, which also I think actually is a 2SC. Often you'll find the 2S is missing. So we can have a quick look at these, see what they measure. Let me just set the camera so you can see the multimeter again. One moment. Got a glare off the screen. There you go. So yeah, so the big ones. I'm in diode mode, and this reads short. Yeah. This is almost certainly the base collector emitter. I'm sure these are bipolar transistors, not FETs, from the 2SC number, but we can check. So they're short, completely short. The little one, which I suspect is to do with the standby supply, and these are two with the main supply. That's reading. Oh, right, that reads a junction there. Normally I'd expect to see a junction from this end, which is probably the base, to both the collector and the emitter. Yeah, and I can see that. And then collector emitter should read open. But we can put the component analyzer on this as well. Let's just have a quick look. We know these are short, so there's no point bothering with them. But let's have a look at this one. One moment, so we at the door. So we put the test meter on here. Sorry about the interruption, guys. I was here for like over an hour. For you it was instant, but for me that was an hour and more ago, so I might have just lost track of where I was a little bit. So we put the tester on, yeah, here, and we can hit test, and it's analysing, and it's telling us that's an NPN silicon transistor. So this is a normal bipolar transistor, not a FET, yeah. Collector, emitter and base, it's telling us the pins, the gain, and the test current, and the base emitter voltage. It tells us a few things actually about this. Various leakage current, there's none, that's good. So that's telling us that's a good transistor. And these two are completely short, so they are bad transistors, yeah. So that's the first fault we found, two bad transistors. What else is wrong with this? And why do I think something else is wrong with it? I think something else is wrong with this because I was seeing a short circuit on the output, and to be quite honest, that transistor, or those transistors short, were on the primary of these transformers. Yeah, they're on this side of the transformer. So they would not cause a short to be visible on the other side. I'm thinking now, I'm just looking at this. Down here I don't see any controller chip to drive any of these. And over in this far corner, this chip, I've looked up the part number, this is a pulse width modulator, a controller. And this is only supposition because I haven't actually tracked this circuit out. But I think that this transformer is a little power supply, and it looks like this transistor connects to that. There's another little transistor here, and I think there's a little circuit here. I don't see a controller IC, but I have a suspicion this transformer, one way or another, powers this chip. And the reason being, on the other side of the transformer, there's another big diode down there, and from this diode to the power pin in this chip, I'm reading through another diode junction. So this seems to be connected to that. Not directly, but seems to be. And I think this transformer basically is not used as a transformer to drive power into here, but is used effectively to transfer a signal, a drive signal from here back to this side. And I think this is the primary and this is the secondary, and this I think drives these big transistors. So I don't see a controller chip here for them, so it must be on the other side. And because one side is completely isolated from the other, the only connection is via the transformers or the opto isolator, yeah? Opto isolators here. So either by the opto isolator maybe, or by this transformer, I think this chip here is driving these FETs. It may be driving them through the opto isolator, which then begs the question, what's the transformer for? And I'm not actually that familiar with this layout. It's a bit of an unusual one, but it's not that important. I am going to find out. I'm going to ask myself how this effectively works, because I'd like to know for my own interest. But what we have, as I was saying, is on the output here, although I've now removed this, I think we'll find we still have a short circuit. In fact, I'm sure we'll find we still have a short circuit. So from black to orange, it's short, yeah? Or very close to being short. That's the 3.3 volts. Yellow I think is a 12 volts. That's okay. Purple is a 5 volt standby. That looks okay. And red is a 5 volt. which looks to be close to being short. It actually has a little bit of a resistance. Let's look at the actual resistance, see what it actually is. 46 ohms, that seems low. And this, 7 ohms, that's much too low. There shouldn't be any shorts like that on there. So, it looks like we probably also have a problem this side of the circuit as well. And once again, the easiest place to find out is going to be to take this heatsink off. There's 2 devices this side, 2 big devices. I want to see what they are. And there's also 2 more on this side I can see down here. They all look to be like transistors or FETs or possibly diodes. Let's see if you can see them. It's hard to see down there, but I think maybe you can just, if we go down from this side, sure there's something down there. This side's a bit easier to see. There's one there, yeah, and there's another one. It's down here somewhere. It's there. See the top of it, yeah, down here, yeah. See 2 there, and I know there's something on this side as well. I can see something there, and it looks like there's something else. Yeah, see the screw in the middle of it there now between the 2 coils. Yeah, so same technique to desolder this one. So I'm going to get that off the board, and then I'll be back to see what we have now. So guys, I now desoldered this heatsink as well. It's a little bit more tricky, that one. I ended up using the vacuum desolder in the end. So on this one, basically, these are all diode networks, yeah. Hopefully you can see the symbol on that one, the diode network. Common cathode, that's another common cathode diode network. So if I zoom this in a little bit more, you'll hopefully be able to see. Yeah, there you go. Should be able to see that with a bit of luck. So yeah, diodes. Each one is effectively a double diode. You can see the symbol there, yeah, at the bottom of it. 2 diodes with the cathodes common on the middle pin. There's another one. Bit of focus on that, it's not quite in, is it? Yeah, that's it. You can even see the part numbers now. So you can see that's a double diode. This one is a double diode. Another one, you clearly see that's a double diode. And that's a double diode. So let's have a quick look to see if there's any shorts here. Let me find the camera so you can actually see the test meter. Yeah, there you go, you can see that now. So let's have a look at them. Put it onto diode mode. Cams fell off again, one moment. There's no glare there, but you can see, okay. So, diode mode, let's look at the first one. So that way nothing. When we put the positive on the end, so effectively the current's flowing in the direction of the arrow, we should get a conduction. You see this is reading lower, the other ones were about 0.4 or 0.5. This is a different type of diode. This is a Schottky or Schottky, not even sure how you should pronounce that, maybe I'll look it up. I call them Schottky diodes, yeah. And Schottky diodes, they're very fast switching, that's the first thing, they switch on and off much faster. When I say switching, when you're in the conducting direction and then you effectively reverse the voltage, it takes a certain amount of time, a finite amount of time for a diode to stop conducting. And this type of diode is very fast, and also it drops less voltage across it, about 0.16 there, yeah. Here's another diode, again same polarity if you like, so black to the middle. So you see that's about 0.4, that's like a normal silicon rectifier. There's another one of the big ones again, probably a Schottky diode. Doesn't conduct that way, go the other way, will conduct. Yeah. In the direction of the arrow from the red, yeah. And this last one, normal diode. So actually, these diodes are all okay. Nothing in that direction, yeah. They're all okay, and yet, when you look at the output of here, I can still see what looks like a short on the 5 volts. and the orange is a 3.3, and the 12 is okay. But I thought that's a bit strange. I went to resistance mode, yeah. I'm thinking, is this like a red herring? Because I can't see unless you've got short circuit capacitors on the board. And I mean, there's lots of capacitors in here. Unless there's a short circuit capacitor with more than one, because on different voltage rails, that seems a bit strange. So I went to resistance mode and had a look again to see what I'm finding. Resistance. So we're going to the orange, 3.3 volts, and it's reading about 8 ohms, yeah, and the 5 volts reading about 46, so it's not actually a short, it's a low resistance again. And I thought to myself, is that normal? Because I don't normally test this. So here's my test power supply, yeah, the ASUS, the one I use on test rig. So let's have a look what we got on this one. So again, this is this one, and I did the same thing on this one, from black, one of the blacks, okay, it's in there, to red is 5 volt I believe, and this is reading about 60 ohms, yeah. Then we go to the orange, and it's not 7 on this one, it's 23. And I'm thinking now, actually, those resistances, camera's fell off, hasn't it? The camera's fell off while I was trying to show you that. Let's go again. From a black to a red, about 60 ohms, yeah, to an orange, about 23. So okay, it's a bit higher than the other one. I'm thinking, well, actually, you know, like whatever I'm seeing that conducting that, 3.3 volts is like on a 7 ohm resistance, that's less than half an amp. So I don't know what exactly really causes that low resistance, but I'm thinking now maybe it isn't actually a fault. If I think it was a short, I'm sure I would have seen it on one of these diodes, and I don't. So this one now, I think we just need to order some of these 2SC 3320s, and then we'll get those here. Let's see if we can actually fix it. Let's see first if these things are quite cheap to buy and easy to get. So we'll go over to the AliExpress. I'm sure I haven't got any of these here. 2SC 3320s. Let's have a look. AliExpress. And let's just put it in. 2SC. Go away, no, we don't want that, don't want that, don't want anything, don't allow anything. 2SC 3320, see what we got. Yeah, oh, 5 of them for €1.50, including free postage, I think, to Spain. 5 for 80 cents. Wow. That looks the same as the ones we've got, yeah. Oh, maybe it isn't, 33.20. Okay, €1.58, €2.50 with the postage. Maybe the one was slightly cheaper. 156, no, with the postage, it's about the same. So about €2.50 I can get those shipped over here. So I'll order a couple of those, and let's see if this is actually something we can repair. Because you know, I mean, it cost me €10. If it cost me another €2, it's worth having. It's a nice little bit of kit, really. So again, you can see they look the same as the picture. They both had some positive feedback, so I think that's okay. Everything else basically checked out all right on this. One moment. Yeah, as I was saying, everything else checked out okay on this. The PFC, we had some funny readings on the diode, but we've explained that due to the short circuit on the transistor over here, so this can go back onto there, that's fine. There's no short circuit on the output diodes. We're seeing some low resistances, but they're a bit like the other power supply, so that may well be okay. There's there, that one goes there, yeah. This one, we need to replace these two big transistors and stick it back in there. And we could have a good working power supply there. It's definitely worth the cost of the bits. So, okay guys, this one's on one side. I'll upload the video and then we'll have a quick resume in about a month's time when I've actually got the parts here. I actually have a few more ATX power supplies hanging around, so please let me know in the comments, would you like me to do a few more of these videos, maybe find some different faults on these? If so, I have some here we can have a play with. Okay guys, see you soon now, bye.